Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. We're in Chapter 3, part of this playlist, which I'm calling Continuous Random Variables. And let's jump to today's topic, which is the beta function. Not the beta distribution. Of course, we'll cover that in a later video, but this is the beta function. Now, the beta function appears in statistics, and knowledge of its properties are definitely important. Now, the definition of the beta function is for any positive numbers, a and b, the beta function, denoted by capital B of alpha b, is defined as this integral. The integral from 0 to 1 of x to the alpha minus 1, 1 minus x to the beta minus 1. Now, let's look at some of the properties. Let alpha and beta be greater than 0, then the beta function is equal to this fraction of gammas, gamma of alpha times gamma of beta divided by gamma of alpha plus beta. And a quick little proof of that is this. So if we multiply gamma of alpha and gamma of beta, now the previous video in this playlist, we went over the properties of the gamma function. And it's defined to be these integrals. Now we combine them, it's the product, and we get this. Now let's do a variable change. Let x equal st and y equal s times 1 minus t. And then when you back solve for s and t, and you solve for the Jacobian, you get s. Now I'm going to let you do that math on your own. But when x and y go from 0 to infinity, then t goes from 0 to 1. And s again goes from 0 to infinity. So notice the limits of integration. And we just plug in what we have here and we get this. Now we're integrating t first. So anything with an s, let's take outside this integral. And what's left. Now notice this here. This is the gamma function of alpha plus beta. And this is how we define the beta function. So if we take this and divide it to the other side, then we've just proved our result. Now, this next result, the incomplete beta integral, is this. So we'll let p be between 0 and 1, and a be an integer from 0 to n. Then this incomplete beta integral, instead of going from 0 to 1, we go from 0 to p of this beta function. But, a and n are integers. That's equal to the sum of these binomial probabilities. Now let's prove this. And now this next page is messy, and I apologize for that. But I encourage you to print it out and leave it on your desk, and people will think you're crazy if you understand it. And you will once we go through it. So we're going to write this left side of this equation. We're just going to use factorials instead of the gamma function. Because everything's an integer, they end up being factorials. Now we're going to repeatedly use integration by parts until this 1 minus y, the exponent goes to 0. So we're going to let u be 1 minus y raised to the n minus a, dv be y minus a dy. Then you take the derivative, and then you take the antiderivative. So this is uv. Now, one note in v, see that a? We're going to add it to one of those, to this factorial, and it becomes alpha factorial, or a factorial, I mean. And in this second piece, now of course we evaluate it from 0 to p, and the n minus a on this piece is going to it's going to take away one of these. You see that here. Now the minus, this usually is a minus, but it cancels with that minus. And this is v du. V, yep. And then du is this piece. Okay. Now when we evaluate this at 0, this goes away. So we evaluate it at P, and I'm going to flash down. It becomes this. We just put P in, okay? And then this piece over here, we're going to evaluate it by integration by parts again. We're going to let U be this 1 minus Y raised to the n minus a minus 1, right? We've just reduced that exponent by 1. And then dv is y to the a dy. That's this piece. We differentiate and we anti-differentiate. And then we plug it in. So this piece, of course, is here. And then this is uv. But notice that the a plus 1 was added to this to increase it by 1. And this n minus a minus 1 reduces that by 1 in this piece here. So in the the VDU piece. Now, when we evaluated at 0, this, of course, that term goes away. So we evaluated at P, and it's just whatever it is. And I'm going to flash it for a second. Now, notice that the part out front can be represented in combinations. So this piece comes down. This piece becomes this piece, right? We just evaluated at P, and this is combinations. Now, this piece, we again evaluate it by integration by parts. And notice that the exponent reduced by 1. So we let u be this piece and dv be y a plus 1 dy. Take the derivatives, du, the antiderivatives to get v. And again, that denominator is going to increase that factorial by 1 on both of those. And this number here, n minus a minus 2, is going to actually decrease. It's going to cancel one of those to get to the n minus a minus 3. Evaluated at 0 goes away. Evaluated at P. Now, to do that, these first 3 terms, we're just going to put in a sum, right? And x goes from a to a plus 2. And we get these 3 terms. And then this 1, 2, 3, 4, the fourth term in this equation becomes over here. Now, if we repeat this, n minus a times, we're eventually going to get that exponent to be 0. And there's going to be this many summations that we have done. We just keep adding to this. And then when we integrate this for the last time, this is 1, it goes away. We get y to the n over n. Evaluated at 0 goes away. Evaluated at P, that n cancels one of those, we get 1, and we can add it to this term. Well, that's what we wanted to show. And the proof is finished. Now, a quick R illustration, and we'll call her quits. The beta function is a built-in function in R. So if we do beta of 2.2 and 4.4, that's equal to the product of these gammas. And notice that they're the same. And this is the formula that we established above. It also works for integers, 2 and 4, and then gamma of 2, gamma 4, and gamma 6. They're the same. But originally we defined beta as an integral. So let's integrate it using 2 and 4 and see if we get the same values. So let's create a function. I call it beta.func. And we're going to create this beta function. X to the a minus 1, 1 minus x to the b minus 1. We're going to integrate this beta func from 0 to 1. We're going to use the parameters a equal 2 and b equal 4, which is what we used up here. And notice we get 0.05. It's the same, as it should be. That's the definition of the beta function. Now the incomplete beta function, let's let n equal 22, a equal 10, and p equal 0.22. If we sum the binomial densities from a to n, we get 0.01226546. But if we integrate this beta distribution from 0 to p with the appropriate shape parameters, a and n minus a plus 1, notice we get the same quantity, as we should. That's what we proved in the theorem.
Okay, we're right at 10 minutes. I'm going to call it quits for this video. Hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.